Good morning. So, welcome to this class on diffractive optics. In this course, we have only a certain amount of time to spend on the different topics. And so, in diffractive optics, we will not cover all the details or the equations, but instead, I want to introduce it to you in terms of how it affects optical systems, how we can use it in a good way, and give you some overview of the applications that diffractive optics is used for. So it's an overview, and I hope it will help you understand diffractive optics in general. Now, till now in this course, we have actually been looking at refractive optics, lenses, or reflective optics like mirrors. How did that work? As a refresher, let's just see. If we had a wave of light, so these blue squares over here indicate the plane, the phase front of that light. If we had a plane wave, so these are the flat planar phase fronts that are coming and are incident on this lens. This is a refractive lens. The shape of this lens is what changed the incident beam, and we went from having a planar wave to a wave with curvature. The curvature, of course, determined by several parameters, some parameters, of course, relating to the shape and refractive index of the lens. In this way, we manipulated the light. We changed the behavior of the light with an optical element, a refractive optical element. What did we look at right at the beginning of the course? We said light travels in straight lines, and you can use a material like glass shaped in a certain way to change that direction. And we saw that Snell's law is what we applied whenever there was an interface. And by shaping the material correctly, we could get the required change. Okay? So what's diffraction? So if you ask someone who's in school, or even people who have come to college and done a little bit of optics, the first answer you might get when you ask what is diffraction is that it is the bending of light. Now, we just saw that when light hits an interface, so you have air and glass, light could bend. So that's refraction. So how do I distinguish this bending of light by diffraction and this bending of light by refraction? Well, the answer really is to go back and see that diffraction is not simply the bending of light. One of the effects of diffraction is that light takes a route or a path that's not intuitive. It takes a path that is not a straight line path as seen or what one expects from geometric optics. One way of defining diffraction then is to actually define it by what it is not. So any bending of light caused not by reflection, not by refraction, you could think of this as diffraction. Okay. Now, while that might be good for a definition, what does it really mean? So to understand that, let's look at three different cases. In all these pictures, you have a plane wave that is incident on an aperture. The only difference between these three pictures is that the size of the aperture is changing. Now, what do we expect from our very simple geometric optics picture is if you have a plane wave of light incident on an aperture, in geometric optics, we assume lambda tends to 0, or in other words, the size of this aperture D is very, very much larger than lambda. In that case, what would we expect if we looked on a screen some distance away? We would expect that in a region corresponding to the opening, to the aperture itself, you would have a region of light and you would have darkness in the regions next to that. So, in other words, you have a perfect shadow in the regions next to the lit region, and the lit region corresponds exactly to the dimension of the aperture. That's what you expect in geometric optics. And if your apertures are very large, that is, this condition is satisfied. That is in fact what you will see. But the moment the aperture starts getting smaller and smaller, and in fact starts approaching the size of the wavelength, you start seeing light in regions beyond. So in this first example, most of the light lies in this region. There's a little spread beyond, but you can see over here where the aperture has become very small, most of the light is in the region beyond. Now, why does this happen? One thing to note is there is light traveling in this region. So there is always some light that is obeying geometric optics. In other words, I can say my systems are always both refractive as well as diffractive. It just can be under certain circumstances, one of these phenomena will dominate. Okay. So let's go back to the question of what is diffraction. We've seen when it occurs. So when you cannot, when this condition is not true, is when it occurs. Okay. So to really understand diffraction, one has to go back to a principle called Huygens wave theory or wave principle. Now, the scientist Huygens, he came up with this hypothesis that you could think of any wave as being constituted of many sources. So I drew this earlier as a plane wave, but you could think of every point, every single point on this plane wave acting as a secondary source. So every point is acting as a secondary source. What does that mean? From each one of these points, you get another wave. And in fact, that's how the plane wave propagates. Now, every point on this will act as a secondary source. So every point acts as a secondary source, and I get another set of waves from these secondary sources, and I have the plane wave. And this continues. Right? But in this ideal picture, if I started out with a plane wave, as the wave travels at any distance, it's going to look very much the same. But what happens when it encounters an aperture? That's what we are concerned with. So let's say I have a plane wave, and now we have an aperture. In this distance, whatever we saw here is what is happening. So the wave travels till it reaches the aperture. At the aperture now, you can consider this region to have sources, the rest are blocked. And for all the sources in the middle, you can consider these travel onward undisturbed. But for the sources at the edge, the wave gets disturbed. And when the wave gets disturbed, in other words, that secondary source is disturbed, the region in which the phase matching condition occurs is now no longer this region, but something like this. In other words, what's happening is light is traveling in another direction. Now, the moment I said you can consider the wave as consisting of a number of secondary sources, you could actually think of this as interference. When we looked at an interferometer, we said take a source of light, split it up into two beams, and then have them interfere. So an interferometer had two beams. In general, when we talk about interference, we talk about a finite number of beams coming together. Because of some difference between these beams, we see some effect, or we exploit and get some use out of that. In diffraction, you can see every point on the secondary source is sending out a wave. All those waves are coherently interfering and causing the next phase front. Every point on that phase front acts as a secondary source. They're all coherently interfering and giving us the next phase front. But the moment there's a disturbance, the waves that get interfering have changed slightly, and where the interference happens, it doesn't happen only in the open region. Somewhere here is where the constructive interference happens, and that's why light leaks into areas which would otherwise have been shadow regions. So I can think of diffraction, if you want to give it another definition, is light it is because of this leaking. I say leaking, but now you should understand that that leaking is actually constructive interference of secondary sources, of light from secondary sources. So it's constructive interference of light from secondary sources, and the place or the places where this happens changes when the secondary sources are disturbed and this happens whenever there's an aperture, especially if the aperture size is in the order of lambda. Okay. Now, let me also allow you to remember something that we talked about in the past. We said, look at a system and let's look at the aberration. So you have, say, an imaging system and you want to create the perfect image. So you have designed your optics in such a way to minimize all the aberrations. If you remember, we said the best you can do is to get a diffraction limited spot. So if I had a beam of light and this single lens here now represents an optical system, if my optical system is perfectly designed and fabricated, I would ideally get a spot of light here. But we always say we get a diffraction limited spot. That is because the spreading of the light, the leakage of the light, of the constructive interference in regions that you don't want there to be constructive interference of light. All of this, different definitions of diffraction, all that they're saying is even if I have the perfect optical system, light is going to spread a little bit. And that's why the focus spot never looks like a point. The focus spot would always be something like this, right? Whereas ideally you would just want something like this. So this is a diffraction limited spot, and you can now understand where it arises from. Because light is interacting with the edges here, you always have finite sized elements and the diffraction effects come into play, and that is why you never get a perfect size spot. Okay. So that's a very simple way of describing diffraction. Who are the people who brought this theory or gave us more background or explanation to this theory? I'll call them the diffractive optics heroes. There are 4 people. There are, of course, many other scientists who are important in this regard, but I've listed out 4 whose names you will see repeatedly if you're studying diffractive optics in detail. The gentleman over here, so this figure over here is from the 17th century. The remaining three are well-known scientists from the 19th century, some of whose names you would have heard. So Fraunhofer, Augustin Jean Fresnel, and Gustav Kirchhoff. These people are famous. They develop many theories of diffraction. And Kirchhoff, you would, if you are an electrical engineering student, you might have heard of Kirchhoff's laws. So he also, of course, did not work just in optics or study electromagnetic waves, but also how voltages and currents in a circuit could be understood or calculated. Okay, so what do we need to understand now, or let's do a quick recap of what I've said about diffraction. Geometric optics, ray optics works fine when you can imagine your feature sizes to be very large or your element sizes to be very large compared to the wavelength. In that case, we say light travels in a straight line, and I go from there and I can use a lot of trigonometry to figure out what happens to the light, and I get very clear, sharp shadows when I block the light in some way. We see, however, that in systems with small feature sizes, small openings, light seems to bend into regions we don't expect it to go, and that is because now the size is affected, the relationship between the size of that feature and the wavelength of the light is actually causing constructive interference from those secondary sources, and that constructive interference takes light into regions that ray optics would not take it. What you have to understand is, I said in the imaging case, I drew a lens like this and I said you get a diffraction limited spot here. Well, you could ask, the lens is large, it's centimeters long, the wavelength of light is in hundreds of nanometers. Why do we see the effects of diffraction here? It seems that the size of the object is much larger than the wavelength. The point is, when light sees the regions near the edge, that edge is acting like the small aperture of the figure I drew earlier. So while the bulk of the lens obeys that its dimension is much larger than the wavelength, this edge effect here, you can't ignore that some part of the secondary wavelengths with regard to the edge of the lens, they are being blocked, and at that point, the dimension being much less than wavelength is no longer true. And that's why even apparently large systems do have diffractive effects. So we have diffraction clearly when feature sizes are of the order of the wavelength. But let's also think of this case. Say you had light coming out of a source. Now, fairly close to the source, the size of that beam propagating is going to be very similar, doesn't change too much. But as we saw with the Gaussian beam, as the beam propagates, it slowly starts growing in size. And we said this is the beam diverging. Why is the beam diverging? Well, again, it's because of these secondary sources, and you're considering the wave from each of them. But as the wave propagates, this is causing more of a divergence. And this divergence is also a diffractive effect. So I can talk about diffraction either because of the feature sizes. I can also talk about it as the wave travels. Because we know only in a plane wave do we say that you have a certain set of secondary sources. But for the Gaussian beam, you can imagine that the secondary sources now don't exist anymore on a flat surface. They exist on a curved surface. And that means the directions in which their resultant wave exists is going to spread into other regions. So as the wave travels, you can consider that as diffraction. So you have two areas or two ways you can consider diffraction happening. It can be just because of the interaction of light with certain sized elements, or it can be just the very travel of the wave that is causing diffraction. Now, to the early optical engineering, diffraction was a problem. You wanted a finite size spot, an infinitesimal peak, focused peak. You didn't get that because of diffraction. That was a problem. You want to resolve two things with a microscope. Because your spot is now spread, you can't resolve that. It affects the resolution. So diffraction was a problem. But I can also use diffraction, because if you think of it, we use refractive elements to manipulate light in a certain way to carry out a certain function for us. What is diffraction doing? Diffraction is changing the intensity and the phase of the light at some plane away from the structure causing the diffraction. What if I create a structure that causes a specific intensity and phase pattern? I can also use a diffractive element, just like I use a refractive element, and have a desired intensity of phase distribution. So diffractive optics, diffraction in an imaging system is a problem, but diffractive optics becomes a tool. Okay. You can think of it as meeting your enemy, your friend, and using that friend. Okay. So think of, you have an incident beam, you now have a diffractive element. This is the diffractive element. We'll see what I mean exactly by the diffractive element. But I'm now going to design this element in such a way that I control the output. I get a desired field. When I say field, I mean a desired amplitude as well as phase. And that desired amplitude and phase, it could be very close to the element, it could be very far from the element, it could be along the axis from the element. It depends on the application that I'm interested in. My goal is to use diffraction to create an element that gives a desired behavior, that is a desired amplitude and phase in the regions after the element. Okay. Just like you think you had an incident beam, you had a lens, and then you focused it. So it was a refractive element, its goal was to focus. Okay. So you might ask though, why use diffraction when I can use refraction? Have these refractive elements, why use diffraction? Well, let's look at some of the issues with refraction. Every time we draw a lens like this, right? Now we might in certain conditions say this is a thin lens, but the fact of the matter is the lens has a finite thickness. It's usually made of glass, so it's slightly heavy. In other words, it's bulky. It's not so easy to manufacture complex shapes. Yes, if I want to manufacture a spherical surface, in fact, we manufacture spherical lenses, even though they're not the best lenses, because that's easy to manufacture. So even if I just want an aspheric lens, it becomes hard to manufacture. And if I want to manufacture something which is more complicated, why? Because I want to create a phase distribution or an intensity distribution that is not just simple focusing, but creates some exotic pattern. It becomes very hard to do that with refractive optics. And again, for refractive optics, I need to pick a certain thickness or shape and refractive index. And we don't have a lot of different materials we can use for refractive optics. So we are very limited in the availability or the variety of N the refractive index. So there are some of the limitations of refractive optics. What do we do instead? We switch to diffractive optics. Now, just to remind you, so it's a small recap. In this course, we looked at light. When we went to the wave theory, we said you can consider it to be a plane wave, a spherical wave, a Gaussian. In all cases, it meant you were talking about an amplitude, a phase, and a polarization. And what is indicated in the figure here is the phase fronts of a plane wave. If I want to engineer a diffractive element, unlike the refractive element, I want to now use fine features, small structures to somehow manipulate light. And we are going to do this. We could play around so that we affect the amplitude. We can play around that we affect the phase of the incident beam. So let's take a structure like this. Let's say I had a structure which had these finite cuboids on it, and I've just shown you a part of the structure. If this was a diffractive element, there would be many more. It's like I've shown you a section of the structure. Designing the element means what is the shape of these structures? What is the refractive index? What are the location? What is the geometry? In other words, what is the height and the width and the length, right? So width, height, length, that is required in order to transform an input beam into some other kind of output beam. So I'm going to use this element now to tailor the incident beam's intensity, its phase, its polarization, even the path it takes, its trajectory. Okay? And as I mentioned, the design parameters can be the lateral dimensions, where these features are located, the shape, the height, the material. Here's an example. This is a cross section of a Gaussian beam. This is, if you looked at the cross section of a beam coming out of a laser, it would have this kind of intensity distribution. You know that, brightest in the middle, tapering off towards the sides. If I put it on a certain kind of diffractive element that was designed to uniformly spread out the light. So the intensity of the Gaussian beam is spread like this, and the intensity of this beam is spread like this. So maybe you are a manufacturer, and part of the industrial process requires to uniformly heat up a patch of metal. If you use this beam, you're heating up the central region more than the sides, whereas if you use this beam, you're uniformly heating it up. What have you done? You have used some diffractive optical element that converts this intensity distribution to this intensity distribution. This is something not easy to do with a refractive element. I could convert this into a ring of light. For example, if we are doing a cataract operation, the surgeon needs to make a circular incision to remove the lens, the eye lens. Now, why heat up the entire region to make a circular incision? You could just use a ring of light. And so, you could use another diffractive optical element that would convert the incident Gaussian beam into a ring of light. So, you by these two simple examples should see that diffractive optics gives you the possibility of creating slightly more complex intensity and phase. In this case, we are only played around with the intensity. I haven't said what is the phase here. But I could also say I have a required phase, and I could use a diffractive optical element to give me a desired phase variation. Okay, and let me skip this part. So, we started out by saying what is diffraction, defining what is diffraction. We said for an optical engineer, diffraction can be a problem because it spreads out the spot or it makes a beam that's traveling through space grow larger. But we can also use it, and if we look at all the beam shaping techniques available to us, you have seen that the refractive optics is what we have spent most of this course talking about. You also have resonators. The way the light comes out, it comes out Gaussian from a source. That is because of the resonator in the laser. So that itself can be thought of as a beam shaping device. And what we will look at a little bit in the next few slides is the diffractive optics. Just for the sake of completion, I also mentioned optics, which over the last decade or so has really revolutionized the way one shapes light, and it has some advantages to diffractive optics. But even to understand that, it's best to go through diffractive optics. So for the remainder of this class, we will look at diffractive optics. So one of the simplest ways of thinking of designing a diffractive optical element is to start with your refractive optical element. So here you have a Fresnel, a plano-convex lens. That's what's shown here. Now, if I look at this lens and I consider the thickness of the lens, what is the thickness of the lens providing in optical terms? As the wave travels through the lens, for a distance corresponding to the, so let's say you have an incident light of wavelength lambda. As it travels through the lens, for every lambda it travels through. In other words, the phase is 2 pi by lambda into n lambda. Every lambda therefore corresponds to a phase change of 2 pi. And we know if light undergoes a phase change of 2 pi, you can consider the value of phase identical to the value of phase it started out with. So that thickness of that lens is not optically actually doing anything for us. So the diffractive optical element just eliminates these extra thicknesses. So this is called a modulo 2 pi operation, where you are dividing the phase in terms of 2 pi levels and removing all the 2 pi levels. So you draw the lines corresponding to lambda, or that is to 2 pi, and this section doesn't play any role, this section doesn't play any role, in this region this section doesn't play, and this section doesn't play any role. And so you just pull out the remaining sections, which is this region here, and this region here, and this region here, and this region here, and this region here. And that is what you get over here. This is what we call a Fresnel lens. Now, it's still not necessarily a diffractive lens, because that is determined by the feature sizes T and D. And the very first Fresnel lenses were used in lighthouses, because you can imagine those lenses are huge, they're meters in diameter, and so the thickness of the glass in the middle was also very much, meaning that the weight of those lenses were very large. So the very first Fresnel lenses were refractive Fresnel lenses, because T and D were still very large, much bigger than the wavelength of light, but you could reduce the bulk of the material. If T and D now start becoming the order of the wavelength, then they become diffractive lenses. Okay, I can use the same technique to convert a refractive prism to a diffractive prism. In fact, we call this a blazed diffractive prism, and you can have a refractive Fresnel prism or a diffractive Fresnel prism depending on these dimensions. So you can immediately see that the amount of material used here and the amount used here or here is far less, which means your element becomes compact and your element becomes less bulky, weighs less. And that's where some of the uses of diffractive optics comes. So, to summarize at this point, diffractive optics works very differently from refractive optics. You are in some sense creating a number of zones in your element, and those zones are creating a number of beams. The final image then is a coherent superposition of light diffracted from those various zones. The so-called bending happens because of the features and the aperture edges, and you can use this now to engineer a desired intensity or phase outputs. What we have seen in the last two slides were the first types of diffractive optical elements that were designed and fabricated. They were all based on refractive elements. You took an existing concept of a refractive element and then did this modulo 2 pi operation and converted it into a diffractive element. But the power of diffractive optics lies in the fact that I can now create any structure, even those that I could not ever do in a refractive sense. I can create any structure, and therefore I can manipulate light in ways that are not possible with refractive elements.